Read this question. In the design of shafts made of ductile material, here the shaft is made of which material? Ductile material, and it is subjected to both twisting moment and bending moment. The recommended theory of failure is, so here for ductile material, which is the most suitable theory is what is asked. See, when it is combined bending and twisting, you need to note a simple point here. See, if I speak of the principal stresses, sigma 1, sigma 2 and sigma 3, let me consider these principal stresses, sigma 1, sigma 2 and sigma 3. Sigma 1 for this case, for this combined bending and twisting, sigma 1 is positive, sigma 2 is negative, and sigma 3 is 0. So for this reason, we can say that the principal stresses are unlike in nature. As principal stresses are unlike in nature, we can say that no two theories will be giving same result. Here I can say that as principal stresses are unlike in nature, maximum principal stress theory and maximum shear stress theory both will be giving two different results. Generally, principal stress theory is used for brittle material. This is used for brittle materials, whereas shear stress theory is used for ductile materials. Remember, if the question would have been as like this, in the design of shafts made of ductile material subjected to pure bending moment, in such situation we will be having only one principal stresses, that can be either sigma 1 or sigma 2 or sigma 3, and other two principal stresses will be 0. In such situation, both these two theories, principal stress theory and shear stress theory, will be giving same result irrespective of the type of material. That can be ductile material or brittle material, irrespective of the type of material, both the theories gives same result. But here, as it is combined loading, combined bending and twisting, as one principal stress is positive, other is negative, third is 0. Remember that these two are going to give two different results, and I can say that the safe result, the best results are given by shear stress theory for ductile materials. So yes, we might have seen that. Yes, you might have seen this thing that when the component is subjected to uniaxial tensile loading, all the theories give same result. If that is given as pure bending moment, then all these will be the answers. As it is combined bending and twisting, the answer for this question is C. The answer for this question is C. Read this question. Strength to weight ratio for a circular shaft transmitting power is directly proportional to. He's asking us to identify the strength to weight ratio. See, what is the kind of strength that he's asking for? It is twisting strength. He's asking us to find the ratio of twisting strength. So let me assume twisting strength by T suffix T to weight. Okay. So here he is asking us to identify this simple ratio. We know that twisting strength is nothing but equal to SYS into polar section modulus. This is divided by, what is weight equation? So we know that it is rho into G, density into gravity into volume. Volume is area into length. We can say that here he's asking us to find this ratio is proportional to, okay, as he's asking us to find the proportionality here, twisting strength to weight is proportional to, I can say that SYS is a constant and rho G are constant, length is also a constant here, length of shaft is not going to change. He's asking us to consider, so how is this ratio going to change with respect to diameter? We can say that polar section modulus is proportional to d cube. This is proportional to d cube divided by area is proportional to d square. So I can say that here d square cancels out. Finally, we get the answer as d. So it is proportional to diameter. So it is not proportional to diameter cube or diameter square. It is proportional to the ratio of twisting strength to weight is proportional to diameter. The answer here is B. Read this question. A large uniform plate, he said that the plate is uniform. Uniform in the sense, what is uniform? Thickness is uniform. Thickness is not going to change. containing a rivet hole is subjected to. See here, so this is the plate in which there is a rivet hole at the center whose diameter is 5 mm given and whose width of plate is given as 10 centimeter. And here it is subjected to uniaxial stress over the ends. As over the end, what is the stress that we have? That is 95 megapascal. See, this stress means what? The load acting on one particle. How many particles do we have at this location? I can say that 95 into area number of particles. Over one particle, the load acting is 95. And here area number. What is the area? Area is 100 mm into thickness. This is the load which is acting on the ends into 100 into T. So this is the axial load which is acting over the ends of plate. And here what is he asking? The maximum stress in the plate is. See, where do we get maximum stress? Maximum stress occurs at minimum cross-sectional region, that is at this region. The plate is subjected to this value of load. We can say that load divided by cross-sectional area. I am going to identify sigma max now. Sigma max as what? What is load here? 95 into 100 into thickness divided by what is the minimum cross-sectional area that we have. So this is 100 mm minus 5 mm. This is 95 into thickness. See how simple this question is. 95 cancels out. Finally, the answer comes out to be 100 megapascal. See, he didn't specify anything about stress concentration factor. I have watched many videos regarding this, saying that there are many videos circulating in the media saying that the answer is 285 megapascal or something else. Remember that as he didn't specify anything regarding stress concentration, it is not necessary to take stress concentration. Remember that we'll be dealing of stress concentration. Yes, if you didn't come across stress concentration, yes, you'll be seeing that topic in second chapter. But remember that here we are not bothering anything about stress concentration. Why? Because remember, if that is not specified in question, will not be bothering about that particular parameter. Okay, so here the answer for this question is 100 megapascal. And one more thing, we'll be saying in detail in second chapter that in second chapter, if the hole diameter is very small compared to thickness of plate, in such situation, the stress concentration for a circular hole is considered as 3. We'll see that, but not in every condition. Why? Because here the size of hole is significant. The ratio of width of plate to the size of hole, or the size of hole to width of plate, is not tending to 0. If that is tending to 0, only in such situation, for a pinhole or a blowhole inside the system, will be considering stress concentration to be 3. For this case, we are not bothering about stress concentration. Keep this point in mind. Read this question. The outside diameter of a hollow shaft is twice its inside diameter. Outside diameter is twice its inside diameter. So we can say that the ratio of di by do, which is equal to k, is nothing but equal to 1 by 2. Okay. The ratio of its torque capacity to that of a solid shaft. He is asking us to identify what is the torque capacity of a hollow shaft to that of a solid shaft. The ratio of that is asked. So for the same material and for the same outside diameter. Observe here. See, he is asking us to identify the torque capacity of hollow member to the torque capacity of the ratio of this is asked. We know that the twisting capacity or twisting strength equation is nothing but equal to SYS. See here, he says that the material is same, so I am not going to change the material. SYS into polar section modulus of hollow member divided by SYS into polar section modulus of solid section. So in numerator and denominator, SYS cancels out. We know that the twisting capacity or torque capacity of hollow to solid is proportional to the section modulus of hollow to solid. What is the equation for section modulus of hollow section? Section modulus, can you please give me this equation? So it is pi by 16 into d naught cube into 1 minus k power 4 divided by pi by 16 into d cube. So for solid member, it is pi by 16 into d cube. That's it. So if you observe carefully, he says that it is same outside diameter. Outside diameter of hollow shaft is nothing but equal to the diameter of solid shaft, which means I can say that these two cancels out. Both are same, pi by 16 cancels out. 1 minus k power 4. What is 1 minus k power 4? K power 4 is 1 by 2. 1 by 2 power 4 is 1 by 16. 1 minus 1 by 16 comes out to be 15 by 16. This comes out to be 15 by 16. Remember that as we are removing some portion of material in hollow shaft, so here there is a reduction in strength. By how much fraction there is reduction in strength? See here, if 16 units is the strength of solid shaft, 15 units will be the strength of hollow shaft even after removing material. Suppose, let me assume that inside diameter to outside diameter ratio is 1 by 3. 1 by 3. In such situation, what could be this answer? 1 by 3. See, k value is 1 by 3. 1 by 3 whole power 4 is 1 by 81. 80 divided by 81 will be the ratio of strength of hollow member to hollow section to solid section. Remember that it generally see here what is constant. Outside diameter is constant as well as the material is constant. In such situation, remember that even after removing a portion of material from the center, yes, there is very slight reduction in strength. That's it. That's the reason why generally hollow members or hollow sections are more economical than solid sections. For achieving this, for extra 1 by 16th strength, or do we need to possess, do we need to give more material? No, not necessary. For that reason, generally what we do is that for most economical design, we'll be considering hollow sections, not solid sections. Okay, remember that hollow one will be having, see, when the ratio of di by do is 1 by 2, in such situation, remember that hollow will be having 15 units of strength, whereas solid will be having 16 units of strength. See, this is a standard one. This can be asked in any examination. So you should be ready with these answer. Okay. So if at all if that is asked in ESE or in your state service examination, you should mark the answer as 15 by 16 directly, and then you need to move forward. Read this question. Two shafts A and B are made of same material and the diameter of shaft B is twice that of shaft A. Diameter of shaft B is twice that of shaft A. Okay, good. The ratio of power transmitting, power that can be transmitted by shaft A to the top shaft B. He's asking us to find the ratio of power transmitted by shaft A to the top shaft B. Now we know that. See, power transmission capacity is, so let me assume that this is the power capacity for a given shaft. So we know that power is generally dependent on torque and the speed of rotation. We know that we can write it as 2 pi n into t divided by 60. We can say that power is directly proportional to torque. See, more the twisting strength, more the power transmission capacity. Okay. So here we can say that power is directly proportional to twisting strength. But what is twisting strength? We know that twisting strength T is nothing but equal to T suffix T. This is twisting strength is nothing but equal to SYS into polar section modulus. See, twisting strength is always proportional to its polar section modulus. So which means I can say that this is proportional to polar section modulus, where polar section modulus is generally proportional, as it is a solid member. We know that it is pi by 16 d cube, right? Okay, so it is directly proportional to d cube. As it is directly proportional to d cube, I can say that power is directly proportional to d cube. Okay, I can say that PA divided by PB is nothing but equal to dA divided by dB whole cube. What is a by b whole cube? So a by b is 1 by 2. So this is 1 by 2 whole cube, which is nothing but 1 by 8. So the answer comes out to be 1 by 8, which is C. Read this question. A solid shaft can transmit. See, it is resisting a bending moment of 3 kilonewton meter, and it is also resisting a twisting moment of 4 kilonewton meter together. So then the maximum torque that can be applied is, so which means he is saying that, so if at all, if we are replacing this shaft by, replacing this combined bending and twisting by pure twisting, so what could be the maximum twisting moment that can be applied? So here we know that, let me assume that corresponding to these two cases, what is constant? We are assuming that the max stress is remaining constant. If stress is remaining constant, I can say that tau max is equal to constant. Tau max is equal to constant. Okay. If tau max is constant, okay, tau max in first case, that is under combined bending and twisting, is nothing but equal to whatever the stress that we are getting in pure bending. Okay, so under combined bending and twisting, what is the equation that we are getting? So for maximum stress, 16T equivalent divided by pi d cube is equal to, so as it is constant, so it is 16T by pi d cube. So this is combined bending and twisting. This is only pure twisting. Okay. Now what is T equivalent? We know that that is square root of, see here, he's asking us to find the value of T. T is nothing but equal to T equivalent, which is nothing but equal to square root of m square plus T square. What is m here? Bending moment is given as 3 square plus 4 square. So what is 3 square plus 4 square? Is that 5 square? So 5 square under root is 5. So here the maximum twisting moment, pure twisting moment that it can withstand is having a magnitude of 5 kilonewton meter. 5 kilonewton meter. This is the maximum twisting moment that it can withstand now. So the answer here is D. Read this question. Which theory of failure will you use for aluminium components under steady loading? See here, he is saying it as aluminium. Aluminium is that a ductile one or brittle one? This is a ductile material. For ductile material, which theory is used is the question. Is that maximum principal stress theory? No, this is generally used for brittle materials, right? Maximum principal strain theory? No, maximum principal strain theory is not used for any material. Maximum or total strain energy theory, this is also not used. So is that maximum shear stress theory? Yes, the answer here is maximum shear stress theory. We know that for ductile materials, two theories are made use. One is conservative theory and the one is economical theory. This is which theory? This is conservative or safest theory for ductile materials. What is economical theory? Economical theory is nothing but total distortion energy theory. Is it right? Yes. So here the answer is, among these four options, the answer is D. Suppose, let me assume that maximum distortion energy theory or total distortion energy theory is also there in the option. In such situation, we need to choose both these two as the answers. See, these kind of questions generally comes in multi-select equation. So if that is coming in multi-select equation, remember that. So maximum distortion energy, if that is there in option C, and maximum shear stress theory is there in option D, you need to choose C and D as your answer. But here the answer is D. Read this question. A small element at the critical section of the component in biaxial state of stress condition is given as, two principal stresses are given, 360 and 140. What about the third principal stress? That is 0. The maximum working stress according to distortion energy theory is, here he is asking us to identify working stress or von Mises stress, maximum von Mises stress. Yes, von Mises stress is nothing but equal to, here this is a maximum allowable stress. Okay, so we know that, so von Mises is nothing but equal to, as two principal stresses biaxial loading, right? So sigma 3 is 0. So we can write this equation as square root of sigma 1 square minus sigma 1 sigma 2 plus sigma 2 square. So here sigma 1 value is given as 360. So 360 square minus 360 into 140 plus 140 square. See here, this was asked for 2 marks in 97. How much easy this question is. Okay. The answer comes out to be, von Mises stress comes out to be 314.32 megapascal. Okay. So here, as the options are given as 220, 110, 314 and 330, we need to choose our answer as 314 megapascal. So this is the maximum stress, which means you can keep our stress a bit below the value of identified stress, allowable stress, which means the answer could be 314 megapascal. With this question, stress concentration in a machine component of a ductile material is not so harmful as it is in case of brittle material. This is a simple question. Actually, he is concentrating under static loading. Under static loading, yes, we know that stress concentration is not that severe in case of ductile materials when compared to brittle materials. What is the reason? We know that if at all, if we have any cut or defect in the system, let me assume that this is the cut. Closer to this cut, in case of ductile materials, yes, will be having yielding closer to this particular region. Okay, here in case of ductile materials, yes, we know that the failure that we are considering is entering into plastic region. If at all, if the load is applied beyond yield point, yes, the component is entering into plastic region. We know that when the stress closer to this cut goes beyond its yield stress, it is entering here the stress. Let me assume that this maximum stress that we are getting due to stress concentration, if this crosses, let me assume that this is going beyond SYT. So SYT in the sense, obviously, if that goes beyond SYT, that is entering into plastic region, which means closer to this cut, yes, in this region, in the vicinity closer to the cut, yes, the particles are undergoing plastic deformation. That's it. The section is not undergoing plastic deformation, only few particles closer to cut are experiencing plastic deformation. That's it. So for that reason, we neglect the effects of stress concentration in case of ductile materials under static loading. In ductile materials, local yielding may distribute stress concentration. Yes, here the answer for this question is, directly we can mark the answer as A. Go to the other options. Ductile material has larger Young's modulus. No, it's not the case. Poisson's ratio is larger in ductile metals. No. See here, all these three options are not speaking of local yielding or plastic deformation in the vicinity of cut. So here the answer for this question is A. Read this question. The process of short pinning increases the fatigue life of steel springs mainly because it results in, we know that the process of short pinning generally introduces compressive stresses in the system. We know that the life of the component, if I draw SN diagram, on x-axis, if I consider log of stress base 10, amplitude stress base 10, and on x-axis log of number of cycles to failure to base 10. If I consider a situation where mean stress is 0, for mean stress to be 0, yes, this is the graph that we get. I'm not considering the material which possesses endurance limit. I'm simply considering a random graph, that's it. Now here, I'm assuming that mean stress here in this case is 0. When mean stress is tensile in nature, mean stress in the sense static stress. Okay, if static stress is tensile in nature, we have identified that the life of the component is going to decrease. Okay, if this is for mean is positive. So when mean is positive, when mean is tensile in nature, there is decreased life of the specimen for the same value of stress. And here you can see that for increased, see, I am considering mean as negative, compressive. Okay, remember that for compressive mean stress, yes, at a given value of amplitude stress, you can see that the life for tensile stress is less compared to no mean stress and compared to compressive mean stress. For compressive mean stress, generally for a given value of stress, the life is increased. Here you can see that he says, okay, here what is the process? The process is short pinning. As the process short pinning, remember that short pinning introduces compressive stresses. Whenever it is introducing compressive stress, only then the life can increase. Okay, among these options, various options that we have, which one is speaking of compressive stresses? Yes, it is option D. So the answer here is D. Residual compressive stresses on the surface. Because of introduction of residual compressive stresses on the surface due to short pinning, yes, the life of these steel springs increases. Read this question. In a shaft with a transverse hole, so there is a transverse hole. Let me assume that there is a shaft here. So for this shaft, okay, here we have a transverse hole at the center, which means there is a hole at the center. So this is a system that is given. I assume this to be a shaft, circular shaft. Now here, so as there is a transverse hole in this shaft, yes, the shaft is subjected to twisting moment. In such situation, he is speaking of stress concentration as a whole to the shaft diameter. What is he saying? Whole to the whole diameter to shaft diameter, which means let me assume that the whole diameter is dh and divided by shaft diameter is d. Okay, if this ratio is increasing, what is happening to stress concentration is the question. If that is changing, what is happening to stress concentration? Remember that whenever the size of cut is very, very small, if I consider the graph between stress concentration, that is torsional stress concentration here, Kt, and on x-axis, if I consider the ratio of dH by d, remember that if the whole size is increasing, always remember, if the size of cut or if the size of defect or if the size of discontinuity increases, always remember that there is decrease in stress concentration. Stress concentration decreases. We have seen this topic clearly. So in that topic, it was clearly discussed that, remember that with increase in size of discontinuity, stress concentration factor decreases. Now here, what is the possible answer for this? So as the whole to the shaft diameter, if that is increasing, if this increases, then the torsional stress concentration factor decreases. Suppose if this is decreasing, so that will be increasing. So I am choosing the answer as increases and decreases. So here the answer is increases and decreases. Read this question. Fatigue strength of a rod subjected to cyclic axial force. Here he is speaking of cyclic axial force is less than that of rotating beam specimen of same dimension subjected to steady lateral force because. So here he is comparing between bending, steady lateral force that induces bending in the system, okay, and he is comparing between axial force. So can you please say me what is the main reason behind this? We know that under lateral loading or bending, we can say that the particles which are far away from, if I consider a rectangle, let me consider the member to be a circular shaft. If I consider this to be the circular shaft, if this is subjected to bending, I am assuming that it is rotating about, it is bending about this horizontal axis. As it is bending about horizontal axis, the extreme particles, the particle which is present at this location, this particle, this is the position of extreme particles from this axis of rotation. Remember that these particles alone are critical. If the particle is taking that particular position, yes, during the rotation of shaft, if that is taking that position, at that particular position, the stress is becoming maximum under bending. Whereas in case of axial loading, we know that every particle at a section is critical. So as every particle at a section is critical, which means the probability of failure happening, is more if the particle, if the component is subjected to axial. Let me assume that. So under axial loading, how many particles are critical? All particles at this section are critical. But under bending, only 2 particles. Now can you please say me in which situation the probability of failure happening is more? Under axial loading. That's the reason why. Mainly it is the reason. Here observe these options. Okay, axial stiffness is less than bending stiffness. It is not the reason. The absence of centrifugal effects in the rod. No, this is not the reason. The number of discontinuities vulnerable to fatigue or more in the rod. Remember that. And the final option at a particular time. Array, this is also not the answer. See, remember that. So, as under axial loading, there are many particles which are prone to failure. There are many, so there are chances that more defects are present inside this cross section. There are more chances of failure. More particles are prone to failure or vulnerable to failure under axial loading. That's the reason why here cyclic axial force, this particular factor is axial factor is lesser than bending factor. So the answer here is, for this question, the answer is what? The answer is C. The number of discontinuities vulnerable to fatigue or more in the rod. With this question, the yield strength of the steel shaft is twice that of its endurance strength. Okay, which of the following torque fluctuations represents the most critical situation according to Soderbergh criterion? Here, as he is speaking of yield strength, so here he is speaking of shear yield strength, that is SY ES is equal to twice its endurance strength, shear endurance strength. This is what is given. And here he is asking us to consider which among the following is the most critical loading condition. Very simple question. See, you don't want to worry at all. Let me give you the logical way of solving this question. Now here, considering these options, we can notice a simple point. What is that? You can notice that the upper limit of load is remaining constant. Is that right? The maximum load is remaining constant. As it is constant, let's see what's happening here. Okay. So which theory he is asking us to consider? Soderbergh theory. Let's choose Soderbergh equation here. So the equation according to Soderbergh is, see, I'm considering now, instead of considering normal stress, we need to consider shear stress here. Tau mean divided by SYS plus tau amplitude divided by ES is equal to 1 by factor of safety. Now, in this equation, I can say that lesser the factor of safety, the loading is more critical. For a critical loading condition, same, if the loading on the component is increasing, the safety will be decreasing and it is very nearing to failure. Okay, which means we need to identify a particular loading condition whose factor of safety is least. But it is not that for each and every loading condition we are going to identify factor of safety. No, it is not the case. Wait for some time. I am going to give you a simple logic. So here I am going to substitute SES as SYS divided by 2. If that is SYS divided by 2, 2 goes to the top. The equation becomes tau mean plus 2 times tau amplitude is equal to SYS divided by factor of safety. Now there is a logic here. Now I need to rewrite this equation into another form. As it is 2 times tau amplitude, can I write it as tau amplitude plus tau amplitude? So can I write like that? Now can you please say me, what is mean plus amplitude? Can I write it as maximum? Yes, we can write this as mean plus amplitude can be written as maximum. So this equation is now rewritten as tau max plus tau amplitude is equal to SYS divided by factor. Why did I write in terms of tau maximum? Why? Because here maximum load is constant. If maximum load is constant here, remember that maximum stress will remain constant. Maximum stress is constant. So here in this equation, this is a constant and SYS material property is also a constant. Now can you please say me factor of safety is dependent on which parameter here? Amplitude stress. As it is dependent on amplitude stress, now we need to choose that particular loading condition whose amplitude stress is maximum. How to identify that? Amplitude is simply if you identify the variation, yes, you'll be able to easily identify what is amplitude here. Now, for the first loading condition, I am considering first loading condition. Observe, For the first loading case, so it is varying from minus t reaching plus t and then minus t plus t minus t plus t. This is how it is varying. Whereas in second case, it is varying from minus t by 2. In second case, what has happened? So it has reached, see, the lower portion is rising a bit. So which means it is varying from minus t. So this is how the variation is. Whereas in the third case, let me choose. Okay, so it is varying from 0 to, this is the variation. Whereas in the fourth situation, final case, can you please say me, that is varying from plus t by 2 to, which means this is the variation. Now you can see that from first case to last case, what is happening? What is happening to amplitude? Is that decreasing or increasing? We are simply decreasing the amplitude. By keeping maximum stress to be constant, we are simply decreasing the amplitude, and we can say that the amplitude for first case is very large. As amplitude is large, when amplitude is large, factor of safety will be minimum. Yes, that particular loading condition is considered to be critical. So here the answer for this question is what? It is A. So these kind of logical questions appear every now and then in GATE. See, you can only tackle these questions if your fundamentals are very much stronger. So what you need to do? You need to make your fundamentals strong. Okay. So the answer for this question is A. Let's understand this question. This was asked in GATE 1887. Very old one, and see how simple this question is. A ductile material having an endurance limit of 196, okay, and yield strength here is given as 294. Somehow it seems like, so these two are multiples of some number, okay. If I notice, this is multiple of 98. 98 twos are, and that is 98 threes are, by the way, I guess. Okay, so anyway, let's move ahead. The maximum and minimum stresses are 147, maximum is 147, minimum is 49. The fatigue stress concentration factor is given as 132. The available factor of safety for this loading is, so here very simple one. Now here we can notice that, so this is 1s are and this is 3s are, okay, 49 3s are 147. So here these are multiples, okay, 49 2s are 98 and 49 3s are 147, okay, that's fine. Now here for this, as these are the factors, can I say that the center value is 98, mean value is 98, and what is the amplitude here? So whatever is the factor that we have, so that is what is amplitude. That's nice. Divided by, so if you notice, so this is mean value divided by SYT, which is 294, plus amplitude divided by SE. What is SE given as? 196. Oh, that's good. Into, see here, he gave stress concentration, fatigue stress concentration factor, right? Now here this is endurance strength, endurance limit. Obviously, considering stress concentration, 196 divided by 1.32. So here 1.32 goes to the numerator. This is equal to 1 by factor of safety. That's cool. Let's see this calculation. 98 1s are, 3s are, as we have already seen. This is 49 1s are, this is 4s are. Okay, anyway, this is 4 1s are, this is 4 3s are 12, and this is also 3, 12. Now here you can notice 0.33 can be written as 1 by 3. And here 1 by 3 is there also 1 by 3. 1 by 3 plus 1 by 3 is 2 by 3. 2 by 3 is factor of safety. Sorry, factor of safety now becomes equal to 3 by 2. So which means 1.5 is the answer. So what is the right answer here? The right answer here is B. See how simple is this? Do we require calculator to this? No, not at all. Let's get into the topic of joints. First, let's solve 1 mark questions and then we'll move to 2 mark questions. So in this, the first question is from GATE 87 paper. Read this question. Weldments in fabricated steel beams are subjected or designed for. So here we are going to design the weld. So in which case? So in case of steel beams. Let me consider a simple steel beam. So let me assume that we have a beam like this, a simple cantilevered beam. a cantilevered beam, and here this is the support. Now here we are going to weld at this location. At this location we have got weld, circumferential fillet weld, and let me assume that the load is applied at this location, at the free end. Now here in this case the weld has to be designed for. If you observe, coolly observe this. So this is considered to be, the load which is acting on this beam is considered to be out plane eccentric lateral load on weld. Now we are designing weld. So if you shift this load from its line of action to weld location, see, we are getting bend moment along with that load. So moment, which kind of moment here? Bending moment along with that load, which means we are designing this weld for two loads. One is bending moment and the one is shear load, which means here the most suitable answer for this case is C. Already have marked the answer. The answer here is C. Read this question. If the ratio of diameter of rivet hole to the pitch is given as 0.25, so what is this given? Diameter to pitch is given. D by P is given as D divided by P is given as 0.25. Wonderful. Now he is asking us to identify tearing efficiency. What is the equation for tearing efficiency? We know that tearing efficiency eta T is nothing but 1 minus D divided by P. In this, already D by P is given. So what could be the answer for this case? So this is nothing but, so if you substitute the same thing, you'll be getting here as 0.75. So where you can write this as 75%. So here what is the most correct answer? So for this, the answer is B. Read this question. So here in this question, he's asking us to identify, so what is happening to bolts in case of rigid flange coupling? The bolts in rigid flange coupling connecting two shafts, so transmitting power or subjected. Let me assume that there are two shafts here. Two shafts are there. So we are considering flange coupling. Coupling is considered here. So I hope so you might be knowing what is a coupling. So it is used to connect between two shafts in series here. So here we have a coupling of this type. So here this is a flange coupling. A flange coupling here. So as we are making use of flange coupling, see here, when the shaft is rotating, see in between these two will be having bolts. So we are connecting these two with the help of bolts here. Let me show you the bolts here. At this location we will be having bolts. We are connecting them. We are connecting them. Now if we observe carefully, let me assume that this driven shaft is stationary. If driven shaft is stationary, if driving shaft rotates, if you observe carefully, the bolts are rotating. If bolts are rotating, see here, sliding. Here, one is sliding with respect to the other, which means here shear is happening in case of bolts. So here the bolts are subjected to shear. See, between one surface and the other surface, you can see that there is shearing action. So because of that reason, here I can say that bolts are subjected to shearing. So which means for sure bolts are subjected to shear. So where do we have shear here? That is an option A. Now here he also gave bending moment. Suppose if both the shafts are already subjected to bending. As they are already in bending, even the bolts will be subjected to bending. Bolts will be slightly subjected to bending. Yes or no? They also will get rotated. Now which means, so in some extreme condition I can say that the bolts are subjected to both shear force and bending moment. So the answer here for this question is what? A. Read this question carefully. Bolts in the flanged end of a pressure vessel are usually pretension. So we are pretensioning the bolts. So in some situation where we have flanged end to a pressure vessel, so you might have seen some pipelines. So in that pipelines, see to that pipes, yes, we'll be having certain flange, and then that flange is coupled generally with the help of bolts. Okay, so we are making use of the same bolts here in case of flanged end of pressure vessel. Okay, their pretension is we are tightening this flanges, right? So we are bringing this two cylinders together, two pipes together. As you are tightening this bolts, what is happening here? Are you avoiding leakage from this pipeline? See, when you are tightening this pipeline, remember that you are trying to avoid whatever the fluid that is flowing inside this pipeline, you are trying to avoid leakage. Is that right? Now here, I can say that. So here he's asking us to indicate which of the following statements is not true. Not true. So let's identify which is not true. So here the first statement says that pre-tension helps in sealing the pressure vessel. So will that seal the pressure vessel? Is that creating any leakage or avoiding leakage? It avoids leakage from the system. So here, which means this is true. This is not wrong, this is true. Pre-tensioning increases the fatigue life of bolts. Obviously, it increases the fatigue life. Remember that there are two conditions. Bolts with preload, bolts without preload. When we are giving preload to these bolts, obviously life increases. Remember that the equation for the resultant load on bolt is nothing but RB is equal to initial load plus C times external load. Suppose if you observe carefully, if there is no initial load, we have seen that the total external load will be acting on bolt. Total, if there is no initial compression between the plates, remember that if plates are trying to get separated, total separating load will be taken by bolts. Suppose if external load is fluctuating, remember that in such situation, when there is no preload, this portion will not be there. So we can say that RB is nothing but equal to FE. RB is nothing but equal to FE. So let me write this equation separately. So resultant load is having two equations, which is nothing but FE. And the one is initial load plus C times FE. And we know that C value is less than 1. So that can be 20% or 30% or 40%. So which means which is very less value. So if you observe carefully, here in this case, external fluctuations are completely taken by the bolt. But here only some variation. See, in this external variation, only some part of that external variation is taken by bolt when there is preload. Which means the variation is small when there is preload. Which means obviously if variation, yes, variation means amplitude. See, variation is nothing but amplitude. If this variation is small, amplitude will be small. If this variation is large, amplitude will be large. If amplitude is small, we know that the life is large. Which means when the bolt is subjected to preload, remember that the life will be more. Why? Because remember that the variation here is getting dropped. Here the variation is more, here the variation is less. Lesser the variation, more the life. Okay, in these two conditions, when the bolt is subjected to preload, remember that it will be having more life. Obviously, this is true. Pre-tensioning increases the fatigue life of the bolts. Right? Pre-tensioning reduces the maximum tensile stress in the bolt. You're tightening. As you're tightening, remember that you're giving extra load, right? Extra load. So with this, so can you please say me, see, this is the equation in case of resultant load which is acting on bolt. Now this is the net load which is acting on bolt. Now please say me whether it increases or decreases. Let's not comment on this for some time. Now let me go with option D also. Pre-tensioning helps to reduce the effect of pressure pulsations in the pressure vessel. Yes, obviously, right? If pressure is changing, so what is changing here? The variation is pressure. If pressure changes, external load changes. If pressure inside the system, pressure is an external load. Remember this point. If external load changes, external fluctuations, remember that because of preload, see, only some portion of this external fluctuation is taken by bolt. See, is this C value smaller than 1 or greater than 1? Smaller than 1. Which means if you see, this is the variation part. Now here in this variation part, see here, this is complete variation. Whatever the pressure that is acting without preload. So this is without preload. So without preload, this is the external load. External in the sense pressure load. See here, if pressure load is varying, this is the varying load. Okay, this is the varying load. Now here if you observe carefully, even though this is the varying load, the variation is this. C times this component is a varying load that we have when there is preload, which means because of this C fraction before this, obviously the variation component, the varying component when there is preload is reducing, right? So which means pre-tensioning helps to reduce the effects of pressure pulsations. This is also true. Now here only thing which is left over which is wrong is C. So here remember that. So you cannot conclude whether it reduces or increases. So that's the reason why here the most suitable answer here is C. Okay. So finally I can say that. So among this the most suitable answer could be C. Let's get into the topic of rolling contact bearings. First we'll start solving 1 mark questions. Then we'll move to 2 mark questions. Here the first 1 mark question is on life. The expected life of a ball bearing subjected to load 9,800 newtons and working at 1000 rpm is 3000 hours. See here he gave life in hours. So can you please give me the equation for life in hours? Life in hours is equal to, so we can write that this is life in revolutions divided by 60N. So this is the equation for life. Okay, so he gave life in hours, and here what is the expected life of the same bearing for a similar load of 4900 newtons at a speed of 2000 rpm. So he is asking us to identify the life in hours. So here the life in hours is equation is this. Okay, that is good. So is this dependent on speed? Yes, if speed is changing, obviously life is going to change. If load is changing, obviously life is going to change. We know that the equation for life in revolutions and C and P. So what is the load life relation? So we know that this equation can turn out to be C by P whole power K into 10 cube divided by 60N. So here from this, can you notice that life is, C is a constant. 10 cube is, sorry, this is not 10 cube, this is 10 power 6. So why? Because life is in million revolutions here into 10 power 6, not 10 power 3. Now here C is a constant, 10 power 6 is a constant, 60 is a constant. Now can I say that life in hours is inversely proportional to N into P power K into P power K. Can I write like this? We can write like that. Okay, so here if I can consider, see here life is dependent on both speed as well as load. Okay, load is changing, life speed is also changing, so life will also change. Now here let me substitute. Can I say that L2 by L1 is equal to N1 by N2 into P1 by P2 whole power K. Let me substitute these values here. So here L2 we need to identify, divided by, what is the value of L1 given? L1 is given as 3000 hours. 3000 is equal to N1 by N2. The speed of rotation in first condition is 1000, second condition is 2000. Okay, so 1000 divided by 2000, 1000 divided by 2000 into, so here load, what is happening to load? Now here you can see that the speed is dropped, so the speed is increasing. If speed is increasing, obviously life will decrease, that we know. But here you can also see that the load is also decreasing. Here the initial load is 9800. Initial load is 9800. But the second load is 4900 only. So the load was dropped 4900 whole cube. What is the value of K? K value is nothing but 3. See why? Because here it is given as ball bearing. The value of K for ball bearing is 3. So here if I consider this to be 3, okay. So here what gets cancelled out? So 9800 divided by 4900. So that is 2 cube. 2 cube is nothing but 8. So here we have 2, and then there it is 4. 4 into 3, 12. So life comes out to be Finally, L2 comes out to be 12,000 hours. The answer to this question is B. So this is how you need to solve such questions. See here in this question, he says that the load on the bearing is reduced to half. Then he is asking us to identify, so what is happening to life? We know that the life and load relation, life is equal to C by P whole power K. Now here if you observe carefully, for ball bearing the value of K is 3. See if at all if the load is halved, okay, which means so P2 is equal to half of P1. Now here if you see that L2, so life is inversely proportional to, right, L2 by L1 is equal to P1 by P2 whole power K. Now here if you observe carefully, what is the value of P1 by P2? P1 by P2 comes out to be 2. So this is 2 power 3. This is nothing but 8. So which means I can say that L2 is 8 times L1. 8 times L1, which means it is increasing by 8 times. So the answer here for this question is A. See here, match the rolling element bearings with the most appropriate loading condition. List 1 is a rolling element, that is the rolling bearing, and list 2 is the type of load that it can take. The first one that he gave is ball bearing. See, did he say that thrust ball bearing or ball bearing? Ball bearing. If that is, if the term thrust is not mentioned, so if that is given as ball, remember that that is a radial bearing. Okay. So here, as there is no term called thrust in this particular statement, I can say that it is a radial bearing. Now here, so let me consider the options here. So a ball bearing is a radial bearing. Okay, roller bearing. You can ask me, sir, why did you choose Q? Why can't you choose R? Heavy radial load with impact. It can take heavy radial load with impact. So why can't we go with that option? Remember that ball bearing possesses a point contact and that can never ever withstand impacts. So remember that because of more contact area, yes, this roller bearing can be subjected to slight impact condition. Okay, but not ball bearing. See, roller bearing can withstand some impact, whereas ball bearing cannot withstand impact. And here, compared to a ball bearing, roller bearing will be having more capacity. So that's the reason why I go with roller bearing as heavy radial load with impact. It can take more radial load as well as slight impact it can also take. Needle bearing. Needle bearing is such a bearing where, so we use this bearing only in such situations where there is limited radial space. So between the shaft and the housing, if we have space, very little space, remember that we make use of needle bearing. Okay, see here in space limitations, space limiting conditions, we make use of needle bearing. So which means C goes to S, tapered roller bearing. Sir, you can ask me, sir, tapered bearing hai na? So if that is tapered bearing, can that withstand radial load? Yes. If there is tapered bearing, can that withstand axial load? Yes, obviously. Now it can withstand both radial as well as axial load. So we can mark our answer here as. So what is the answer that we can choose here? So tapered roller bearing can withstand heavy radial and axial loads. So here, as there is no term called a thrust, remember that still it is a radial bearing. If at all, if that is given as thrust tapered roller bearing, then it is an axial bearing where it can withstand more axial loads. What is the difference between a radial bearing and an axial bearing? The bearing which can withstand more radial load is a radial bearing. The bearing which can withstand more axial load is an axial bearing. So if at all, if the term thrust is mentioned, that will become an axial bearing. Why? Because so it can withstand more axial loads than radial loads. Understand this simple point. Now here the answer is Q, R, S, T. So in a sequence. Okay. So this is the answer. A goes to Q. So B goes to R, C goes to S, and D goes to T. So this question, spherical roller bearings are normally used. So why do we make use of spherical roller bearings? Generally, these are used to withstand or to compensate for misalignment. These are simply the rolling elements which we have will look like a barrel. Barrel in the sense, in Pirates of the Caribbean, you might have seen the crude oil barrels, right? So we call that as a bulged cylinder. See here, the rolling element is considered as a bulged cylinder. So here, for that reason, remember that. So mostly, majorly, these are used to compensate only for angular misalignment. So these are not the answers for this. So for increased radial load, for increased thrust load, when there is less radial load, these are not the suitable answers for this. Remember that it is only used to compensate for angular misalignment. See this question. In this question, he is asking us to identify what is the basic load rating of a ball bearing. What is the meaning of load rating here? Remember that it is generally considered as the maximum radial load that the bearing can withstand for a rating life of 10 power 6 cycles. So here I have used a term called rating life. So what is the meaning of rating life? See, at a particular value of load, generally a bearing fails at a particular speed of rotation. See, as if I consider 100 identical bearings, all these 100 bearings, identical bearings, will not fail at the same speed. They'll be failing at different speeds. Let me assume that we have some range of speed. So let me assume that 100 bearings will be failing within this range of N1 to N2. So somewhere in between these N1 to N2 cycles is at a particular value of load, they can fail. Now here, the meaning of rating life is, see here, the meaning of rating life is, so 90% of the bearings will live for this particular life condition. Let me assume that, so if I see, before N1 cycles, no bearing will fail. After N2, no bearing will live. So beyond N2, no bearing will live. Before N1, no bearing will fail. This is what is the condition. So which means if I increase the value of life, if I consider more and more life, remember that the possibility of failure of bearing increases. Now here, rating life is such a life where 90% of the bearings will withstand, will satisfy that particular life, will live that life. Only 10% of the bearings will fail. Our condition for rating life is 10% can fail and 90% should live. Okay, for 90% life, of the bearing, yes, remember that we are considering the life as rating life. So which means, let me assume that corresponding to this condition at this particular location, whatever the life that you are considering, that is represented by L10, remember that this L10, so if I consider the life to be L10, only 10 bearings under that load will fail. In 100 bearings, only 10 bearings will fail and remaining 90 bearings will live. That is what is the meaning of life L10. Now here, let's see what is the right statement for right condition for load rating. Maximum static load. It is not the maximum static load. No, we are not speaking of a static load here. So which means this is a wrong one. It is not a static load that the bearing can withstand plastic deformation, blah, blah, blah. Wrong. The radial load at which 90% of the group of apparently identical bearings run for 1 million revolutions before the first evidence of failure. Oh, yes, this is almost closer to the statement which we have seen. It is the maximum radial load that the bearing can withstand for a rating life of 10 power 6 cycles. 10 power 6 cycles in sense 1 million revolutions. 1 million revolutions. And what is the meaning of rating life? So rating life is 90% will live. 90% of the identical bearings will run or live. Yes, that is also getting satisfied. Both are same, right? So rating life, and here instead of giving it as rating life, he has given it as a statement, which is true. Now here directly I can mark my answer as we don't want to worry about the other two options. You have got your answer, so you can mark your answer, you can move forward. But anyway, let's see the other two options as well. The maximum radial load that can be applied during operation without any plastic deformation. No. It is corresponding to fatigue failure. Remember that this load rating is corresponding to fatigue failure, not corresponding to plastic deformation under static loading condition. Combination of radial and axial load, no. Plastic deformation, this is also wrong. So here the answer for this question is B. Let's move to 2 mark questions. So here the first question is from GATE ME paper to the 1997. The dynamic load capacity of 6306, 6 in the sense the term 6, the initial 6 represents a deep groove ball bearing, single row deep groove ball bearing. 3 represents the capacity of this bearing, dimensional capacity of this bearing. So more the dimensions, more the value of 3. So more the second number. 06 represents the bore diameter of this bearing. Okay, so here 06 when multiplied by 5. So obviously the shaft is having a diameter of 30 mm. So here we have got the simple understanding from this data. Now here it is having a dynamic capacity of, it is a ball bearing, 6306 in the sense it is a ball bearing, single row deep groove ball bearing. Remember that. Then this particular number is very, very important. Okay. The maximum radial load that it can sustain to operate 600 revolutions per minute at 2000 hours. Sorry. Yes. Okay, here he is asking us to identify maximum radial load that it can sustain, and here he also gave the life in hours. How to solve this question? Now let me consider the simple analysis. So we know that life in revolutions is nothing but C by P whole power K into 10 power 6. And we can also write this in terms of life in hours as life in hours into 60 into N. This is a simple equation that we have. Let me substitute all these values, all the details to get my answer. Okay, the value of C is given as 22 divided by, we require this value of P, maximum load that can be applied to get the life as 2000 hours. So whole power 3 into 10 power 6 is equal to life in hours. The required number of hours here is 2000 into 60 into the speed of rotation is given as 600 revolutions per minute. 600 revolutions per minute. Here it is already given. Now here if you solve this, see here 1, 2, 3, 4, 5, 6. So it is gone. So if you solve this, you will be getting your answer. The value of P comes out to be here. So P comes out to be 5.29 kilonewtons. Why is this in kilonewtons? Why? Because already he gave the value of dynamic capacity 22 kilonewtons. As this is 22, obviously this will also be having, P will also have a unit of kilonewtons. Okay. So the answer here for this question is what? Answer is D for Don. See this question here, he is asking us to match the list 1 and list 2. So here he is asking us to consider, in list 1 he is asking us to consider automobile wheel mounting on axle. See, we have an axle and then let me assume that wheels. So wheels, are they taking radial load? Yes. So when you are maneuvering, remember that, are they taking some kind of axial load? So do they take any amount of axial load? Yes, they also withstand, they also take or bear axial loads. Obviously, we'll be having gears, right? Obviously there. So we need to make use of some combination bearing, that can be angular contact bearing or tapered roller bearing. So which one shall we make use of here? So here, as it is an automobile, obviously the capacity should be large. So for more capacity, see here, he also gave high speed grinding spindle. See, when you are grinding, remember that here you will be applying some radial load as well as axial load. Both will be there in case of grinding spindle. See, we keep the member at some angle. As you are trying to keep the member at some angle, so it results in both radial as well as axial load on the shaft. Obviously, the member has to withstand both radial and axial load. Now here, compared to, so automobile wheel, remember that here in this case, lesser loads will be present. Now here, in these two, the race is present. Now here we have got angular contact ball bearing, tapered roller bearing. Now for which among these two shall we give angular contact ball bearing, and for which one we'll give tapered roller bearing? According to me, I need to choose my answer for automobile wheel as tapered roller bearing. Okay, whereas for grinding spindle, I need to choose it as angular contact ball bearing. Whereas in case of IC engine connecting rod, there will be having huge impact, huge thrust. There you can neither use ball bearing nor you can use roller bearing. Now here only bearing that you can use is, yes, that is a bush bearing, which is nothing but hydrodynamic journal bearing. Remember that in case of IC engines, so we generally make it at connecting rod location, we need to make use of journal bearing. This is good, well and good. Whereas in case of leaf spring eye mounting, so at the location of eye mounting of leaf spring, at that location we need to make use of bushes, rubber bushes will be there, right? So bush mounting has to be present. So here I can say that we need to make use of Teflon or nylon bushes in case of eye of a leaf spring eye. Okay, so these are the various options that we have. These are matching that we have for where A goes with tapered roller bearing, which is 3. A is 3. A is 3. B is 2. C is 4. D is 6. So this is your answer. Rate this question. If the life of a ball bearing at a load of 10 kilonewtons is 8,000 hours, its life in hours, if the load is increased to 20 kilonewtons, keeping all other conditions to be constant. See, load is doubled. If load is doubled, what is the relation between load and life? We know that the life equation is life is equal to C by P whole power K. K value is 3 for ball bearing. So here he says that it is ball bearing, right? Now here both are, so L is inversely proportional to P cube. If load increases by 3 times, life will decrease by 8 times. So here, if load is doubled, remember that life will drop by 8 times. Okay. Now here, the original life is 8,000. So 8,000 divided by 8 is 1,000. So the answer here for this question, very simple, direct question. This is C. Let's get into the topic of sliding contact bearings. First, we'll move with 1 mark questions. Starting friction is low in. Among these 4 different options, he is asking us to choose one bearing in which one condition where starting friction is very low. So here, if you observe carefully, hydrostatic lubrication. So what is hydrostatic lubrication? So remember that in static condition, if you are trying to rise a shaft away from bearing surface, then we are going to call it as hydrostatic lubrication. Under static, there is separation. So when you are separating this in static condition, remember that obviously as it is getting separated, there is no metal to metal contact. There is no rubbing action between the surfaces. Obviously, in such situation, as in static condition, it is rising away from bearing surface, is the friction will be low, and then you require very less effort to rotate that particular shaft. Okay, hydrodynamic lubrication. Hydrodynamic lubrication in sense, under static condition, there is direct contact. Okay, and then in later contact you are rising the shaft away from bearing surface. Now here in case of hydrodynamic lubrication, yes, starting friction is very high. Why? Because there is direct metal to metal contact. Mixed or semi lubrication, mixed lubrication. So even in mixed lubrication, there is metal to metal contact. Boundary lubrication, where boundary lubrication is nothing but thin film lubrication condition. So where there is direct metal to metal contact. See here, all these are the results of boundary condition and mixed lubrication. These two are the changes that we obtain under hydrodynamic condition. In the initial condition, there is thin lubrication. Keep this point in mind. Remember that Hydrostatic lubrication is such a lubrication where even in static condition, even in starting condition, there is separation, and then you can smoothly rotate even in starting condition. So here the answer for this question is A. See here in this question, in thick film lubrication, in thick film hydrodynamic journal bearings, the coefficient of friction when there is thick lubrication, in case of journal bearings, radial bearings, is asking us to identify. So what will happen to coefficient of friction with respect to load? We know that in case of thick lubrication, in case of journal bearing, whenever the hydrodynamic bearing attains thick lubrication, yes, according to Petrov, we have some condition. We know that according to Petrov, mu equation is mu is equal to, where coefficient of friction mu is equal to 2 pi square into Zn by P, where Z is viscosity into R by CR. See here, P represents pressure, bearing pressure. Now, if you observe carefully here in this case, he says that coefficient of friction is it dependent on pressure, is it dependent on load or not? Increases with increase in load, is independent of load. Remember that. So this is an invalid option. That is dependent on load. So may increase or decrease with increase in load. We can also eliminate this. See here, increases or decreases. This is what we need to identify. So here with increase in load, if load increases, remember that coefficient of friction decreases here. So pressure, load increases, pressure increases. If pressure increases, friction decreases. Here we can say that. So decreases with increase in load. So the answer here for this question is C. See this question. To restore stable operating condition in a hydrodynamic journal bearing when it encounters higher magnitude loads, so what should happen to viscosity? So here we need to write some relation between load and viscosity. Load and viscosity, let's make some relation. So here when it encounters higher magnitudes of loads, right? So we know that the equation, the relation mu is equal to 2 pi square into Zn by P into R by CR. Now here, if I draw the graph here between Zn by P, so in x direction we consider Zn by P, and in y direction we consider coefficient of friction. Now here if you observe carefully, so I am considering thick region, thick lubrication region. In this thick lubrication region, this is the equation, this is the condition that we have. So when it encounters higher magnitudes of loads, remember that Zn by P value is, what is happening to Zn by P value? So Zn by P, see if P increases, higher magnitude Zn by P decreases. P increases, Zn by P decreases, which means it is moving in this direction. And then coefficient of friction decreases. When coefficient of friction, if this is decreasing, remember that. Yeah, sorry for that. So here what is happening? If load is increasing, coefficient of friction is decreasing. Now for stable operating condition, Zn by P should remain constant. See, to keep this as a constant, to bring back to original condition, original position of mu, remember that there has to be rise in the value of Zn by P. If Zn by P has to be risen, remember that, so what should happen to Z value here? So Z value should also rise. Z value, Z rises, viscosity rises, then only mu will remain as constant to achieve stable condition or original operating condition. Remember that Z should rise. See here, remember this is the direct, what is the relation that we have between P and Z? Direct relation. As loads are more, remember that viscosity should be, oil viscosity is to be increased here. Now here, He also says something about oil viscosity index. So what is viscosity index? Viscosity index is considered to be the parameter which represents the variation of viscosity with respect to temperature. How well the viscosity changes with temperature is what is said by these two parameters. We are not worried about these two parameters. We are worried much about, here in this equation, worried much about viscosity itself. Viscosity itself. So here the answer is oil viscosity is to be increased. The answer here is B. Let's get into the topic of clutches. Now we'll see 1 mark questions. So we have only few 1 mark questions here. So only one question we have here. Actual operation clock clutch having a self-locking tooth profile. See here, he is asking us to consider something. So he is asking us to consider which clutch? Axial operation, jaw clutch or claw clutch. So here, in this case, he is asking us to identify, so here self-locking tooth profile having. So can be disengaged. So can we disengage that system at any speed? Or can be disengaged only when unloaded? No. Can be engaged only when unloaded? No. Can work only with load. See here, the thing here is, so in case of jaw clutch, see, as these two members are moving by the process of interlocking, remember that at any speed you'll be able to simply disengage the system. If you bring the driven shaft away from the driving shaft, remember that there can be disengagement here. But engagement cannot happen at any speed, but disengagement can happen at any speed. See, you are driving your bike. You're driving your bike. Let me assume that you have decelerated and then you have, can you lower the gear? Or let me assume that you are driving a car. When you are driving a car, so that can be you might be in any speed, that can be 100 or 200 or 300, so which you might not be going. Actually, let me assume that you are going at an economy speed of 80 kilometers. And then you in the top gear, if you bring that to neutral, so even without holding the clutch, so can you bring that to neutral? Yes, you can do that. Okay, even at 80 kilometers per hour, you can bring the gear lever from 5th gear to neutral. So in case of cars, right, similarly, even here we can disengage the system because of interlocking here as they're rotating here. Remember that. So we can disengage the system even at any speed. If you are moving this away, disengagement can happen. Okay, interlocking will be lost. Okay, so if they are interlocked, yes, there can be torque transmission. Interlocking will be lost, remember that, at any speed of rotation. But locking cannot happen, interlocking cannot happen at any operational speeds. Remember that if driving shaft is rotating at 5000 rpm, so if you bring the driven shaft closer to it, this driving shaft will completely destroy the driven shaft. Why? Because driven shaft is already at rest. Okay, remember that for smooth engagement here, remember that both has to be rotated. So both should be rotating at same speed. If driving shaft and driven shaft, if both are rotating at same speed, then we can engage system. There should not be any relative rotation between driving shaft and driven shaft to engage between driving and driven shaft. Keep this point in mind. Now here, so as he's speaking of disengagement can happen at any speed and can be disengaged only when unloaded. No, it is not necessary. Only in unloading condition. Yes, even in unloading condition, disengagement can happen, but also in rotating condition, disengagement can happen. Okay, so here he says can be is a possibility, can be disengaged at any speed. That can be at resting condition or at moving condition. He is saying that disengagement can happen. Now can be engaged only when unloaded? No, even when, see here, even when it is loaded. Remember that if both are rotating at same speeds, as we can engage the system. So which means this is also wrong. Can work only with load. Now here the most appropriate answer here among these 4 options is can be, the answer here for this question is can be disengaged at any speed. So this is your answer.